In this video series, we have talked quite a bit about building machine learning models. However, another important step is explaining the output of machine learning models. This can be a useful diagnostic for the data scientist to get an intuition for how their model is making decisions and whether or not that makes sense. It can also be a useful tool to gain buy-in from stakeholders. Now, we have to be careful exactly what we present to stakeholders. Of course, we should always be transparent and honest. I'm not saying that we shouldn't do that. What I am saying is that we should not present overly technical model explainability charts to them, because that's not going to help them at all. That's actually going to confuse them and have the exact opposite effect of what we want. But again, model explainability can be used for the data scientists and also for external partners as well and stakeholders if we know how to use it properly. One methodology that I like is called SHAP, SHAP, and this is model agnostic. So this is something that you can easily look up yourself and see how it works. We're not going to dive into the mathematics of it yet, but it is a very useful methodology. And again, it's model agnostic. And we can actually use SHAP to explain functions that are not machine learning, things that are more generic as well. So I have the documentation popped up here. We can see that, for example, this is for census income classification with light GBM, and this does something that we've done pretty close to what we've done in this course so far, where we load in a data set, we build the model, and then we see the output. So in this case, this is explaining the predictions for light GBM, which is a type of boosting model. So if we scroll down, we can see all kinds of neat and useful charts that can help us understand what our model is doing and how it's making decisions. So these do not necessarily have causal understanding unless we're doing true causal modeling. This is still connection between variables. And for that reason, I like to give a portfolio approach to model explainability. So I like SHAP. We'll dig more into SHAP here in a minute, of course. But I also like drop column importance and permutation importance. And those are concepts that you can research and learn on your own. So I like to see if there's agreement among these methodologies and what differences I see and why might those differences be occurring. So there's not one true best model explainability technique. We should use a portfolio of approaches. And again, those are different topics for another day. And in this video, we're mostly just talking about the application of SHAP values. So one of the things about SHAP is that your code will be slightly different depending on, is this a classification model? Is this a regression model? In some cases, there's special handling for boosting models. There are slightly different cases for how you would handle a calibrated classifier CV. So what I've done is I built a Python library called SHAP. And what this will allow you to do is just drop in your model and your data, and then it will produce the SHAP values for you. And this will also, under the hood, in cases where it's appropriate, apply multiprocessing as well. So basically, this is just a wrapper for Python SHAP's library that basically provides a nice level of abstraction, or I hope a nice level of abstraction, and as appropriate will apply multiprocessing, where as the initial SHAP implementation is very good, but it does not provide multiprocessing natively. But SHAP is something that will automatically kick in multiprocessing when it's appropriate. So how do we actually use SHAP? Well, we can, again, just drop in our model and the data we want to explain and get out SHAP values df, which has local explanations, our SHAP expected value, which is just the, in the case of classification, that is the percentage of occurrences in the positive class. So that's kind of the baseline value. And then the global SHAP value. So that is not what is happening on a local explanation. That is, on average, how much does this feature contribute to predictions in the data set that I am explaining. So in SHAP, there also are ways to get output plots in CSV files, so you would call it produce SHAP values and summary plots. But in this case, we're just going to return the raw data itself. So we can see that ran okay. I'll go from bottom to top. So on the bottom, we have the global SHAP value. So again, this would be on average, this is the contribution of worst perimeter to the prediction function, which is producing the likelihood of having breast cancer. The SHAP expected value is just the percentage of cases in the positive class. So this is just kind of the baseline. And again, really what we're doing in a tree-based model is we have everything as an initial group, and then how do we create segments based on the data that move us as much as possible away from this mean value. And then we talked about local explanation previously. So this output gets truncated a little bit, but we can see that for the first row in the data set, this is the contribution of each of these features to the predicted probability of being in the positive class. So we can see that whatever the value of mean radius was, that decreased the likelihood of having breast cancer by 2.5% or 0.025 negative. So again, this is just kind of an easy way where you can drop in your model and then your data and get out this output without having to write a lot of boilerplate. If you want to know more about SHAP, you can definitely dig into the documentation, but this is just a way that you can use SHAP. One other thing that I'll point out, which is a little bit of a gotcha, is that let's say we have a pipeline. So we cannot actually throw our pipeline into AutoShap, nor can we throw our pipeline into the initial, or the, I shouldn't say initial, I should say the original SHAP library itself, which is just SHAP, is how you would pip install that. So what we have to do is we have to rip out our pre-processing and then rip out our model and then apply our pre-processing, and then when we generate our SHAP values, we just pass in the model that we ripped out from the pipeline. Now, this is pretty simple. This only has one pre-processing step, but if we had multiple pre-processing steps, we would have to make sure to apply those as well. So this can be a little bit complicated depending on what all is in your pipeline. Most of the time it's pretty straightforward though, but this is a little bit of a gotcha in the fact that you have to make sure that whenever you're using SHAP, in this case, we can't pass in this full pipeline. We just have to pass in our fitted extra trees model. So let me run this. So the first thing I print is the original X test, and then below that, I print X test after we transformed it. So at this point, we have gotten our X test into the shape that it would be going into the step in the pipeline or going into the model. So we have to make sure that X test applies all the pre-processing that's necessary if we've stuffed it in the pipeline. And then below that is just what we've seen before. So local SHAP, the expected value, and then global SHAP as well. So we can recollect that these are similar to what we saw above, but again, we have a slightly different data set because we did a train test split, so that would explain why these numbers are not exactly what they were previously. Again, if you want to know more about SHAP, definitely research on your own. I think this is a great methodology as part of a portfolio for model explainability, and I've built the AutoShap library as a way to reduce some of the boilerplate when producing SHAP values.